In this video, we are continuing to look at Activity 1B on heat equations and calorimetry. And so we're going to start off with number 7. It says how many joules are required to heat 75 grams of water from 100 degrees Celsius to 185 degrees Celsius. And it says the heat capacity of steam is 1.84 joules per gram degree Celsius. So we know water, once it reaches 100 degrees, that's when water starts to boil or vaporize. And so when we are heating water from 100 degrees up to 185, it's going to be in the vapor phase. So we need the heat capacity of steam or water vapor. So in this problem, it says how many joules, so that's going to be our value of Q, that's our energy, which is equal to M times C times delta T. So we have Q, whoops, we don't actually need to do Q, we need M equals C, and then T final, T initial, and delta T. So our mass is 75 grams. Our C is 1.84 joules per gram degree Celsius. Our T final, we're going from 100, so that's our initial, to 185, so that's our final temperature. So 185 minus 100, that's 85 degrees Celsius for our delta T. So now we just need to substitute into our equation Q equals 75 grams times 1.84 joules per gram degree Celsius times delta T, which is 85 degrees Celsius. So we just need to substitute or plug into our calculator now. So Q equals 75 times 1.84 times 85. And that gives us 11730, and then grams cancels, degrees Celsius cancels, so this is in joules. So Q equals 11730 joules. And of course this is being absorbed. It's required to heat up the water, which is why it comes out as a positive value. On to the next problem. It says, what is the specific heat capacity of a metal if it requires 177.7 joules to change the temperature of 15 grams of the metal from 25 to 33 degrees Celsius? So this time we're asked to find specific heat capacity, which is C. So Q equals M times C times delta T, but we need to rearrange this equation to solve for C. So we'll do that by dividing by M and delta T, and of course what we do on one side we need to do on the other side. M delta T. So M cancels out, delta T cancels out, and we're left with C equals Q divided by M times delta T. So now we just need to figure out what all these values are. Our value of Q is our amount of energy, requires 177.7 joules. Okay, our value of M is 15 grams. And our value of delta T is going to be T final minus T initial, which will give us delta T. Let's see, so 25 degrees is our initial from that, 25 degrees Celsius to 33. So that's our final temperature. And then our change in temperature is 8 degrees Celsius. So now we just need to substitute in. C equals Q, 177.7 joules, divided by M, 15 grams, times delta T, 8 degrees Celsius. And of course our units, none of them are going to cancel out, so our units on our answer will be joules over grams times degrees Celsius. So let's plug this in to our calculator. We have 177.7 divided by 15 times 8. And that gives us 1.48 joules per gram degrees Celsius. And I'm just going to leave it just like that. Box that answer in and we are done. The last problem on this sheet says, what is the specific heat capacity of a metal if it requires 90.2 joules to change the temperature of 25 grams from 22 to 35 degrees Celsius. So this is a very similar problem to our last one, just different values, a different metal, I suppose. So specific heat capacity, we're searching for that. So I'm going to use the same rearranged equation, C equals Q over M times delta T. So I need my Q, M, T final, T initial, and that of course will give me delta T. Write out all my variables. If it requires 90.2 joules, so that of course is my Q, 90.2 joules of energy, to change the temperature of 25 grams, so that's my mass, from 22, so that's my initial temperature, to 35, so that's my final temperature. And so of course to get delta T, I'll do 35 minus 22, which I'm not confident in my math abilities right now apparently, so I'm doing that in my calculator, 13 degrees Celsius. And I just need to substitute into my equation. C equals 90.2 joules divided by 25 grams times delta T, which is 13 degrees Celsius. So if we plug this into our calculator, we get 90.2 divided by 25 times 13. And that gives us 0.2775, which I'm going to round to 0.278. And of course my units are joules per gram degrees Celsius. And that is my value of C. So box that answer in there. This next problem says a 50-gram sample of metal was heated to 95 degrees Celsius and then quickly transferred to an insulated container containing 50 grams of H2O, or water, at 25 degrees Celsius. The final temperature of the water was 30 degrees Celsius. What is the specific heat of the metal? So this problem, where we have a metal or something be heated up and then transferred into water, and then the temperature is allowed to equilibrate, and we're measuring the final temperature, this is a calorimetry problem. So calorimetry. So anytime you see something being transferred to an insulated container and it's asking you to find the final temperature, that's a calorimetry problem. And in this case, we are using the fact that whatever heat leaves one thing is going to enter the other thing. So in this case, we have a cup of water that's at some temperature, and then we put a hunk of metal, which is hot, into the water, and the heat from the hot thing is transferred from the hot thing and into our water until the temperature of the metal dropped into the water is equal to the temperature of the water. So when we measure the final temperature of the water using our thermometer, which I'm not a very good drawer, but we measure our final temperature of the water with our thermometer, we can assume that the metal is also at that same final temperature. So this is the final temperature of the water, 30 degrees, but that's also the final temperature of the metal as well. T final of the metal as well, because they're going to end up at the same temperature. It's like when you go outside and your hands start off nice and warm, but then they gradually get cold. That's because your hands are losing heat into the cold air around you, because your hands have more heat than the air, so the air is sapping the heat away. It's pulling the heat away from your hands, or the heat is moving into the air. The heat energy, or energy in general, always moves from high concentration to low concentration. So when you have lots of heat in your hands and the air doesn't have as much heat, nature tends to equilibrate that situation. The heat from your hands moves into the colder air to create a sense of equilibrium. So that's what's happening here. So we have kind of two situations going on. We have all of the variables for our water, and then we also have all our variables for our metal. So for our water, we have our Q, we have M, C, and then T final, T initial, and delta T, of course. And then we also have all those same variables for our metal. So I always kind of like to make a T-chart here to keep track of all my variables. We have those of the water and those of the metal. and this just helps me stay organized to figure out what I have and what I need to solve my problem. So let's just go through the problem and fill in all of the pieces of information we do have. So a 50-gram sample of metal. So that's my mass of my metal. So metal, mass, 50 grams. Was heated to 95 degrees Celsius. So 95 degrees Celsius, that's my initial temperature of my metal, 95 degrees Celsius. And then quickly transferred to an insulating container containing 50 grams of water. So there's my mass of my water. At 25 degrees Celsius, there's my initial temperature of my water. The final temperature of the water was 30 degrees Celsius. So I know that's my final temperature of the water, but then I also know that the metal is going to have an equivalent final temperature because heat is going to continue to be transferred from the metal to the water until they reach the same temperature. So that final temperature is also the final temperature of the metal. What is the specific heat of the metal? So we know the problem is asking us to find C of our metal. So I'm going to put a question mark there. So we know that that's what we're trying to solve for. So we have a lot of information, but we also have a lot of missing pieces of information. So let's figure out which ones we know on our own. So I think, okay, I don't know the specific heat of the metal, that's what we're looking for, but I do know the specific heat of liquid water. That's my value, 4.186 joules per gram degree Celsius. So now I have my T final and my T initial for each thing, so I can also find my change in temperature. So 30 minus 25, that gives me 5 degrees Celsius, and 30 minus 95, which I'm going to put in my calculator just to make sure I do it right, gives me negative 65 degrees Celsius. So I have MC and delta T for the water, and then I have M and delta T for my metal. So I know that the amount of heat that's given off by the water is going to be equal to the amount of heat absorbed by the metal. So if I can find the amount of heat energy that's absorbed by the water, oops, I think I said that backwards before, the amount of heat absorbed by the water is going to be equal to the amount that was given off by the metal. So if I can find this value of Q, I know that this is just going to be the same value with an opposite sign, and then I can use that to solve for my value of C. So this is kind of an interesting situation. We first need to solve for the Q of the water. So then we know that the Q of the metal will equal the Q of the water. We know Q water will equal the Q of the metal just with the opposite sign. So if I can find Q water first, I'm going to find this first. Then I can use it to help me determine the specific heat of water. So I'm going to first find the Q of the water, then I'm going to know the Q of the metal, which will help me find the value of C for the metal as well. So let's start by solving for Q of the water. So QW equals M times C times delta T. So this is all for the water, so 50 grams times 4.186 joules per gram degrees Celsius times delta T, so 5 degrees Celsius. So my degrees Celsius cancels, my grams cancels, I'm just going to have joules. So let's get a calculator. 50 times 4.186 times 5. And that gives me QW, which equals 1046.5. And that's joules. So I know that my Q of my metal, QM, is going to equal the same value, just negative. So negative 1046.5 joules. So now I can use this value to help me find my value of C. So I just need to take my equation, Q equals MC delta T, and rearrange it to solve for C. So Q equals Q divided by M delta T. M cancels, delta T, that equals C. So C, now I'm just going to plug all these values in, equals the Q of my metal, C of my metal equals Q metal, so negative 1046.5 joules divided by M of the metal, so 50 grams, times the delta T of the metal, which is negative 65 degrees Celsius. So my negatives will cancel out because I have one on top, one on bottom. So I'm just going to do negative 1046.5, whoops, and 1046.5, close parentheses, divided by 50 times, and I'm going to open a new set of parentheses, negative 65, close parentheses, close my denominator, hit enter. And that gives me a value of 0.322, and my units, of course, are the long units of joules per gram times degrees Celsius. So that is the specific heat capacity of my metal. So just to quickly recap what we did here, first, we looked at our problem and we listed out all the pieces of information that we had in the problem. Then we figured out that we do know the specific heat capacity of water, so we can use all this information to solve for the amount of energy that's absorbed by the water. And we got that value. It was 10, and I'll fill that in now, just in a different color so we can remember what we had. We got that value. It was 1046.5 joules. And we know that the energy that's given off by the metal is just the same amount of energy, just negative. So we put negative 1046.5 joules, and then we used this value to help us solve for our specific heat of our metal just by rearranging our equation here. And last but not least, we have number 11, which says a 20-gram sample of iron at a temperature of 120 degrees Celsius is placed into a container of water. There are 300 milliliters of water in the container at a temperature of 30 degrees Celsius. Given the specific heat of iron, which is this, calculate the final temperature once the water and the iron reach an equilibrium temperature. So this is another calorimetry problem. We have a metal being put in a container of water, and we're actually already given the specific heat of the iron. It's asking us to calculate the final temperature. So this, I'm just going to warn you, this is going to take a lot of algebra here. So we have our Q, which equals M times C times delta T, and we have this for our water, so M water, C water, delta T water, and then we have the same Q of our metal equals M of our metal times C of our metal times delta T of our metal. But the problem with this is we can't just solve for one Q and then find the other Q because we don't know the final temperature. So the delta T of our water is going to be the final temperature minus the initial temperature of the water. And the delta T of our metal is going to be the same final temperature minus the initial temperature of the metal. So in order to solve for this final temperature, we're going to have this variable on both sides of our equation. And let me just show you how this looks like when we set it up. So we know that Q of the water is going to equal the negative Q of the metal. It's just going to be the same value, opposite sign. So instead of having these values of Q in, we can just go ahead and say that the Q of the metal is going to equal negative M times C times delta T, all of our metal. So I'm just going to nix these Q's. We're going to say they're equal to each other. So I'm going to have M of the water times C of the water times delta T of the water equals M of the metal times C of the metal times delta T of the metal. So this doesn't look too bad yet, but unfortunately we have to expand our delta T to be T final minus T initial. So I need to expand this a little more. So this part is now going to be T final minus the T initial of the water. And this part is going to be T final minus T initial of the metal. So this gets a little confusing here. So now I'm going to go ahead and bring down the rest of our equation. So TW, delta TW, I've expanded to T final minus T initial. So I have the water mass and the water specific heat times T final minus T initial of the water equals negative mass of the metal times C of the metal times T final minus T initial of the metal. The reason I don't need to put T final water and T final metal is because these two values, these two final temperatures, they're going to be the same thing. Because we know that when we drop a piece of metal in the water, heat is going to transfer from the metal into the water until they're at the same final temperature. So these two things are going to be equal. So I need to find out all these other variables, substitute them in, and then solve for T final, which will be on both sides and will be the same thing. So let's start listing out our variables here, because there are just a lot of variables. So we have water, and then we have our metal, and we have Q, M, C, T final, T initial, and delta T. Which our delta T, I guess, is not going to be so important in this case because we already had to expand our equation out. So, Q, we decided that Q of the water is going to equal the negative Q of the metal, but we're not actually given either of those values. We'll leave them in their variable forms. I need to move this up a little bit so you can actually see what I'm doing, but we'll have to keep moving it up and down so we can also see the problem. So a 20-gram sample of iron. So that's our mass of our metal, 20 grams, at a temperature of 120 degrees Celsius. So that's our initial temperature of the metal. Is placed in a container of water. There are 300 milliliters of water. So this is kind of tricky, but a milliliter of water is equal to 1 gram of water. So they're trying to trick you, but 1 milliliter for water is the same thing as 1 gram. But this is only for H2O. But it's a useful fact to know because this comes up a lot in chemistry where we measure the volume of water. We don't actually get out a scale, but we don't have to because we know that 1 gram of water is the same as 1 milliliter. So 300 milliliters is the same thing as 300 grams of water. And it's at a temperature of 30 degrees Celsius, so that's my initial temperature there. Given the specific heat of iron, so 0.444 joules per gram degree Celsius, 0.444 joules per gram degree Celsius, calculate the final temperature once the water and the iron reach an equilibrium temperature. So this T final is what we're trying to calculate, and we know that T final of the metal is going to be the same as T final of the water. So I'm going to substitute in a variable that seems more simple than TF. I'm just going to put an X. So those are both X. And then, of course, my specific heat of my water is 4.186 joules per gram degree Celsius. Okay, so now I have a whole lot of variables. I need to substitute some of them into this equation that I have to use up here. All of our variables set up, we just need to plug into this monstrosity of an equation. So I'm going to move this paper up so we have plenty of room. So we need the mass of the water, so 300 grams, times the specific heat of the water, 4.186 joules per gram degree Celsius, times T final, so we're using X minus T initial, 30 degrees Celsius, equals negative of the mass of the metal, so 20 grams, times the specific heat of the metal, 0.444 joules per gram degrees Celsius, times T final, X minus T initial of our metal, which is 120 degrees Celsius. Oh, and I've actually already gone off the page. So as you might see, it's a little bit confusing, for me at least, to look at this with all of my variables, my X, and also all my units. So when I'm going to rewrite this, and I always like to show my units to make sure I can keep track of all of them, but I'm going to rewrite this without units, because when we're doing algebra, it's a lot easier to look at an algebra problem without a whole bunch of units to throw you off. So I'm going to rewrite this, 300 times 4.186 times X minus 30 equals negative 20 times 0.444 times X minus 120. Okay, so now this looks a little bit easier for me to look at. So I'm going to go ahead and multiply some things out, so that way we can make this problem look a little bit simpler. So I'm going to go ahead and do 300 times 4.186, and that got me 1255.8 times x minus 30. So I just combined these two numbers here, and that equals 20 times 0.444. And of course the 20 was negative, so it's negative 8.88, those two numbers, times x minus 120. So next I'm going to go ahead and distribute. So I'm going to do 1255.8x, 0.8x minus 1255.8 times 30. So 1255.8 times 30 is 37674. These are big numbers, but it's really not that complicated. We just have really big numbers that we are working with here. So don't let it scare you. Now I'm going to distribute the other side. So negative 8.88x, and then negative 8.88 times negative 120, which is going to give me a positive number. So 8.88 times 120 gives me a positive 1065.6. Okay, so that looks a little bit simpler. Now I'm going to combine some of my like terms. So I have negative 8.88x, so I'm going to add this to both sides. Plus 8.88x. So these cancel out, and I have 1255.8 plus 8.88. 1264.68x minus 37674 equals just 1065.6. So I'm making this problem look simpler and simpler. Now I just need to combine my non-x terms, so plus 37674 plus 37674. So these cancel, and I'm going to have 1065.6 plus 37674, which gives me 38739.6 on this side, and that equals 1264.68x. So now all that's left is I just need to divide by this number to get x by itself. So divide by 1264.68, 1264.68. So x equals this divided by that. So this divided by 1264.68 gives me 30.6319. So after all that algebra, I just need to go back and figure out what my x was meaning. Sometimes it's easy to forget. So my x was my final temperature. So I'm going to go ahead and put T final equals 30.6319, and then a temperature, my units, should be degrees Celsius, but we can go back and look at our problem to figure that out. There will not be a problem like this on your quiz, but it's always good to challenge yourself and try problems that just contain a little bit more complex mathematics.